Okay, so last time we were talking about the integrated and differentiated power series, right? So you start with the power series, you differentiate it, and you integrate it. And it turns out those things have the same radius of convergence. That being said, they generally have different domains of convergence. Okay, so what happens at the endpoints can actually change, right? Like they don't have to be the same. So, okay, that's an interesting thing. But what we still need to do is relate these power series back to the original function. So if I say I've now got a function and I defined it in terms of its power series, right, on its domain of convergence or on its interval of convergence. If I define a function like that, is it differentiable? Is it integrable? And are these equal to, is the power series representation of its derivative equal to the differentiated power series? Is the power series representation of its integral equal to the integrated power series, right? These are the sorts of questions that we want to ask. And we know that there's some trickiness here, right? I mean, pointwise convergence certainly doesn't preserve differentiability, and even uniform convergence doesn't preserve continuity. So, there's a little bit of an issue there. Now, let's see. Yeah, okay, sure. So let's do exactly what I said. Let's prove that. So here, I need the theorem statement in front of me because one of them is slightly different and it's kind of annoying that way. So theorem. So let's say if the sum of, what have I been using? CK? I think I've been using CK, XK, K equals 0 to infinity, has radius of convergence R. And we define a function like this. And again, right, you sort of know what this function is going to be. Then f is in fact differentiable. And what we want to be true is true. Okay. So you differentiate, right? You set this thing to be a function. That thing is differentiable, which again is kind of surprising because we know that generally doesn't have to be true. It is differentiable and its derivative is equal to the differentiated power series. And the main crux of this is if you think back when we were talking about uniform convergence, we did have a theorem which told us when differentiability was preserved, right? It said, if you know that the f's are differentiable, the fn's are differentiable, and they converge uniformly to a function, and then you know their derivatives also converge uniformly to a function, then the original function was differentiable, and whatever the derivatives converge to was equal to that derivative. And because these power series are basically just polynomials, right? Their partial sums are just big polynomials. Those are all differentiable. So everything we need to apply that theorem is actually true, right? So let's say, proof, fix some x in a minus r, a plus r, and choose, little r such that this is true, right? And again, we're just doing this so that we can actually get the uniform continuity uniform convergence, because we don't know that we get uniform convergence on all of the interval, right? We might have to restrict a subinterval or some subinterval. This should be x minus a. I've already started, too late. So I guess we're actually going to do this one with x minus a. Okay. And so what do we know? So we know 1, the partial sums, k equals 0 to n, ck x minus a to the k converge uniformly to f, right, on a minus r, a plus r. All right, we proved that last time. And two, I guess, maybe let's call these d's for like differentiated, right? K equals 1 to n, k, c, k. Oh, and I guess, and maybe I should say here, and each Sn is differentiable. Right? Because again, it's just a polynomial, right? It's written sort of in a weird way, but it's just a polynomial. And these dn's, x minus a to the k minus 1, converge uniformly to some function, right? Because it's within the radius of convergence, right? Because the differentiated power series has the same radius of convergence, and we've restricted to a smaller subinterval. It uniformly converges to something. We don't know what it is. To some function g on a minus r, a plus r. Okay. So by our previous theorem, this is enough to show that two things. One, f prime is differentiable. And it occurs to me, actually, now that I'm thinking of it, I might have stated in that theorem, I might have forgotten, I might have assumed that the limit was differentiable, but you actually don't need it. You can actually prove it. And the proof just like the proof of that theorem doesn't change at all. But anyway, these are the two things that we need to prove that f prime is differentiable, to apply that theorem. So immediately we now get f prime is differentiable and its derivative is equal to the differentiated power series on the interval a minus r to a plus r, the little r here, right? So applying a previous theorem, and if you don't remember what theorem it is, yell at me and I'll dig it up, I'll find it. So applying a previous theorem, f is differentiable and f prime is equal to g, right? Do you remember that sort of statement there? So f prime was equal to whatever this function g was, but i.e. it's convergent, right? This is what the differentiated power series converges to. So yeah, no problem. That's exactly what we wanted, right? F prime is equal to the differentiated power series. And this is what we wanted to show. Now we've only shown it for the interval, a minus little r to a plus r, but like we've basically now shown it for that particular choice of x that we had. And of course, as we let r sort of vary, I can then do this for any x, right? So thus the theorem is true. On a minus little r to a plus little r, and by varying little r, we get that it is true on the whole thing, right? And again, if you don't quite see that last part is true, eventually, like effectively what I did is up here, I said, fix some sort of x. Like what I've really done here is proven the theorem for that x, right? I've proven that, yes, the function little f is differentiable at this point of x, and it's differentiated, like its derivative has this power series, right? So I haven't I've kind of very quickly expanded that and said, hey, listen, it works on a minus little r to a plus little r. But if you really are worried about whether or not this is true, recognize that because differentiability is a local condition, right? We talk about being differentiable at a point, then you can say, hey, listen, I'm going to prove that this function is differentiable literally anywhere on this interval. How do you do it? Well, pick a point, right? Call it x, and then pick some little r between, the absolute value of x minus a and big R. And now you've proven that differentiability for that point. Since that point was chosen arbitrarily, you've done it everywhere, right? So that's why when we sort of oscillate, or rather when we vary this little r, we can actually get the whole interval, right? We said the same sort of thing for continuity, right? The best we could do was guarantee continuity because we only had uniform convergence on this a minus little r, a plus little r. So the best we could do was sort of continuity on that restricted interval, but because I can, we talk about being continuous at a point, I could do that for an arbitrary point, and therefore I could do that for every point. And that's why we were able to extend that to continuity for the entire function. And exactly the same thing is happening here, okay? So we're able to do differentiability for the entire function. So does that make sense? Are there any questions about that? Like basically just, we're in such a great situation that these functions are so nicely behaved because they're just polynomials, right? The partial sums are polynomials. Because they're so nicely behaved, we sort of immediately pick up what we want. And in fact, what you can probably imagine is you can now bootstrap this, right? Like, all right, what about the differentiated power series? Well, that thing has the same radius of convergence and, converges uniformly on any smaller subinterval and is still just a polynomial. So this function is actually twice differentiable, right? And the second derivative is the second differentiated power series. But that thing has the same radius of convergence and converges uniformly, and its partial sums are polynomials. Exactly, this thing actually has to be C infinity, right? Whatever this function converges to is actually C infinity. So that's a cool thing, right? Like that's bootstrapping, that's that induction, right? Nothing here actually restricts it from being C infinity because we can just do this process as much as we want. And that's, again, something that's really afforded to us by the fact that these are polynomials, right? At the end of the day, that's what these things are. So between that and uniform convergence, we get what we want. And of course, we can go the other way too, right? But like, that's not as surprising. Like we can integrate it as many times as we want. Well, it's not even that we're taking C1 implies it. It's that these things are polynomials. And because they're, partial sums are C infinity, basically we get C infinity from that. Do you know what I mean? So it's not like we're having to assume C1. The idea is that we get C1 automatically because they're polynomials. And because they're polynomials, that, do you know what I'm saying? Like we're not taking that assumption. We're not proving if you're C1, then you're C infinity. It's you're C1 period because you're a polynomial. And therefore you actually have to be in C infinity. Whatever this thing converges to must be nice. And that's not going to be crazy. When we do sort of the reverse direction, we do Taylor series, we're going to say we have to work with C infinity functions in order for that to be true. Blah, 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 blah. We get F is. So you said Fn converges to F uniformly, Fn and F are differentiable, and blah, blah, blah. But we get, right, okay. So Nicole, actually, I think I misstated that theorem. So if we go back and we dig that out, do you remember, Nicole, which day that was? So I don't think it was Tuesday. Was it last Thursday? Oh yeah, here it is. So it's true. Actually, remember how I said I think I misstated this theorem? And the reality is I did. Okay, so we don't actually need this. So what do I want to cross out here? So let's cross out then F is differentiable. And this is true. And again, so in our sketch, the proof, you can actually see that nothing changes in the proof, right? So here, if I show that this limit exists, that is the proof that F is differentiable, right? Like this left-hand side here is actually the definition of the limit for the, the difference quotient of F. So if I show that this thing is less than epsilon, that actually proves the differentiability of F, right? So I sort of jumped the gun there in that we didn't actually need that. And then if you look at my epsilon over 3, none of these require that F is differentiable, right? So I misstated this theorem because we don't actually need the differentiability of F to prove it. And in doing the proof, we actually proved that F is differentiable, right? So yeah, that's my bad. I did misstate that theorem. But this was, and for the record, everyone, if you were sort of confused about which theorem we were using, this is that theorem that we were using, right? Yeah, exactly. Each Fn is differentiable. Yeah, which we do get, right, in that other example, because again, they're all polynomials. So we get that each of those was differentiable. Right, and they're differentiated power series. We're again still polynomials. So they, and they have the same radius of convergence. I guess that's really the more important thing. They have the same radius of convergence, and because we were looking at a smaller subinterval, they also converge uniformly. Okay, everyone's good? So yeah, 100%, that was my mistake there. I misstated that theorem, but there's the fix to it, okay? And like I said, you can see we don't use the fact that f is differentiable actually in that proof, and we actually prove that f is differentiable in that proof. So that's sort of nice. Okay, so that's it for the derivative. Now the integral we're going to do, that's the next one. So the integrated power series. So theorem, blah, 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 right? If this is a thing, has radius of convergence big R, and we define this function, a minus big R, a plus big R. I guess I did define what balls were, right? I could actually just replace this with a ball here. Then f, so then actually, yeah, here's what I want to say. So here we have to sort of do a stupid little tricky thing. Then for all R in R satisfying I guess this should be strictly positive here, R less than R. F is integrable on a minus R, a plus R. And on that interval, what do I want? So the integral from a to x, f of t dt is equal to the sum from k equals 0 to infinity, this thing. Okay, yeah, exactly, the R ball center today. We totally talked about that thing. So I could have written it down, right? Instead of just writing a minus R, a plus R every single time. Okay, so the reason that we get this sort of annoying thing here, so notice this theorem is slightly different than the differentiability statement, okay? And the reason for that is, again, we can talk about what it means for a function to be differentiable at a single point, right? And then we say that it's differentiable in general if it's differentiable at all the points. But the continuity and differentiability are things that are defined at single individual points. Unfortunately, integrability is not, right? We don't talk about a function being integrable at a point. We talk about it being integrable on an interval. I guess I should really say, closed interval a minus R to a plus R, but whatever, it doesn't matter. So because when we talk about integrability, we need to actually talk about it being true on an interval. We have to sort of, we're not going to be able to do that thing that I'd done previously where we just said, hey, fix an X and make sure it lives in an interval in which you converge uniformly. Unfortunately, we're sort of not going to get, a theorem as nice there. We're sort of restricted to doing this sort of interval trickiness in order to get our uniform convergence. Because again, that's what we need, right? We need our uniform convergence in order to ensure that the integrals of these things actually converge. And yeah, and actually I have a really fun story about this that I'll tell you when I'm done. Okay, so fix at 0 less than R less than big R. So these partial sums converge uniformly, right? Ckx minus k to the k converge uniformly to f. Okay. Now we said as well, right? Exercise, prove that whatever these things converge to is also integrable, or I should say on, on a minus R, a plus R. So they converge uniformly, which means not only are they, is the limiting function integrable, but the antiderivatives also converge, right? And that's it, we're done. Thus f is integrable. on a minus r, a plus r, right? Uniformly convergent limit of integrable functions is integrable. This was an exercise that I left you all to prove that I hinted would be very, very important. So thus f is integrable on a minus r to a plus r. And again, like we have that the integrals of the fn's converge to the integral of f. Right? But this is exactly what we want. This is precisely the statement that the integral from a to x of f of t dt, right? So that's the right-hand side, is the limit, right? As, well, I guess as n goes to infinity of the integral from a to x, let's say Sn. So I'm just like, hopefully you maybe see this immediately, but you know, if I sort of write it out here. To show you kind of the important part of what's happening. Because, so normally you can't pass a limit inside of an integral sign, okay? That's a tricky thing and you can't do it. But that's fine, we don't actually need to do that because this is a finite sum, right? And we know that the integral is additive. So because this is a finite sum, I can actually take the sum outside, and that's going to be enough. Oops, so CK, I guess I could take the CK out too, but whatever. Oh, sorry, I guess these should be T's because I'm integrating with respect to T. So CX, and then yeah, you like, we know how to integrate polynomials, right? And that's what we wanted. Okay, so you don't have to go into that like much detail. In some sense, I would have been happy if you just said, yeah, and so we're done. But I wanted to show you like really why it worked. And because it can sort of feel as though we're pushing a limit inside of the integral sign, and we're not, okay? Again, when you want to push a limit inside of the integral sign, you need big theorems in order to be able to do that. That's generally quite tricky to do. But that's not what we're doing because these partial sums are all just finite sums, right? Then yeah, you can totally take the sum out of the integral sign. So it's not that I'm pushing the limit into the integral, I'm actually taking the sum out of the integral, right? And again, I can do that because it's a finite sum. And voila, now I win. So the only reason I wrote out that much detail is you could see I wasn't pushing the limit inside, I was actually taking the sum outside. Okay? So then, yeah, this is great. So just sort of like as a very quick example, you can do already some surprising things with this. So we could say like find a power series representation for, I don't know, what do we want? Arctan? Arctan. Right, on some interval, whatever interval we want. Arctan, okay, really it does have to be on, for arctan on -1, 1, okay? And that is very kind of suggestive of what sort of thing we're gonna do. Now, for us right now, right, because think about how we're studying it. Right now, we're sort of starting with a series and then trying to figure out what function it's equal to. And next week, we're going to do the opposite. We're going to start with a function. We're going to try and find a series. But for the most part, right now, we only really have one series that we understand really, really well, right? And that's the geometric series. right? So we know 1 over 1 minus x right? So this thing has radius of convergence equal to 1. So these two things are actually equal on -1 to 1, right? So now we have to be a little bit tricky. We say, well, okay, how can I relate this to arctan? Well, note that the absolute value of x is less than 1 if and only if the negative x squared, well, what do I want to say here? Which direction is going to be true here? Yeah, so -1 is less than x squared is less, negative x squared is less than 0. That's going to be true, right? And so this number is still in the regime where we can apply the geometric series to it. We're going to have to check my logic here in a second to make sure that I didn't actually want to go in the other direction. But 1 over 1 plus x squared, right, is then equal to this thing. Right? So basically, if I choose some x between -1 and 1, and I take its negative x squared, I'm still in a regime where I can apply the geometric series, right? Like I haven't broken that. If my absolute value is less than 1, then x squared of me is also less than 1, right? In fact, it's even smaller than whatever x was. And then I throw a minus sign in front of it. So, okay, whatever. It's between -1 and 0, but I'm still in a regime where I can apply an infinite geometric series. Okay, so this identity is true. Does everyone believe that? Everyone's good? Okay. And now if I integrate, so this, again, this is still true for x between, right? And now I can integrate this. That's true, right? But according to my theorem above, and again, sort of this thing where I do have to actually look at what some smaller r's, but I'm not going to worry about that right now. We can think about the logic of that later. And voila, I now have a formula for arctan. Somebody double check my integration though, just make sure I did that right. So I think that's pretty nice. And here's something else that's cool. Once you have this series, now I wouldn't suggest that you actually use the series for this, but once you have the series, you can approximate pi, right? Because what do we want here? Arctan 1 is what, pi over 4? Yeah, I guess I can't do that. I need a smaller one. Can anyone give me one? What's arctan? What are some nice values of arctan? Does anyone remember? If we draw a triangle. Okay, what are our triangles here? So we have our boring, stupid triangle, but what is this? 1 over root 2, oops. Oh man, I've forgotten my special triangles. That's embarrassing. What are my special triangles? Somebody remind me. That would be root 3, but I don't think that's the special triangle I want, right? Oh man, that's how long it's been since I've done trig. Well, yeah, that's going to be a thing. Okay. All right. Let's just Google it. Right. It's 1 root 3 and 2. Thank you. Okay. 1 root 3 and 2. This is pi over 3. And this is pi over 6, right? So if we do arctan, so opposite, adjacent, I guess I can't really avoid that. But 1 over root 3 is in this regime, right? So if I did something like arctan, but 1 over root 3 isn't, oh, no, well, it's not as nice. Is there a better one I can use? So root 3, all right, that's not, I don't think that's the one I want. Pi over 4, pi over 4. Damn, that's not gonna work either, right? Because I'm gonna have to plug in arctan 1, and this doesn't work outside of there. Okay, here, let me show you in theory what we could do here. So we might need to be a little bit more clever about how we do this. Oh, you know what though? This thing totally converges at 1, right? Okay, hold on. Arctan 1. So even though 1 is not in the domain of or is not in the radius of convergence, it is in the domain of convergence, right? So note that the sum from k equals 0 to infinity, -1 to the k, 2k plus 1 times 1 to the power of 2k plus 1. This thing converges, right? This is just the alternating series test. Right? So that thing totally converges. But that's going to be equal to arctan 1. I mean, technically, we do need a theorem that tells me that this function is equal to what we want it to be on its boundary, but that thing's called Abel's theorem, and it's a little bit hard to prove. But this is also equal to pi over 4. So what you have now, if you, so again, I am sweeping a little bit of stuff under the rug here, that the function is actually equal to what you want it to be at the boundaries, right, on the domain of convergence, because we don't have any theorems which state that. But now, all of a sudden, I have a series representation of pi over 4. And that means that I have now a series representation of pi, right? Because if I multiply both sides of this equation by pi, now this is not a good approx, like, you know what I mean? This converges very slowly, because we know that the harmonic series converges, like the alternating harmonic series converges very, very slowly. And this is in some sense worse, right? Because I'm actually only taking the odd term. So this converges very, very slowly, but nonetheless actually gives you a way of computing pi, right? Because you just decide how many terms of this you're going to use. Like, let's say you add up the first 100 terms of this thing, and all of a sudden you get a pi out, right? So, I mean, again, there are much better ways of doing this than this, but yeah, this is a way that you can actually compute pi, right? So that's a thing. That's a thing that you can do, which I think is kind of cool. Right, yeah, right. The right-hand side is like perfectly nice. You know, it doesn't look gross at all, and yet somehow this thing converges. And go ahead, plug it into Wolfram Alpha, and assuming that I haven't made an obvious mistake, ask it to compute the first 100 terms. And again, you're going to have to like really use a lot of terms here for this thing to converge, but ask it to compute the first 100 terms of this thing and see if it converges to pi. Now, I was asked to do, so that's it for the lecture today. I was asked to make a comment. Let me sort of like give a big major hint here. So this, somebody asked me for problem set 14, like A14 extra 3. And right, okay, so this is a phenomenal question. So you're told that AK is a sequence such that the limit, I strongly recommend everybody pay attention. No, just AN. AN plus 1, no, AN minus 1, sorry, AN minus 1. 2 is less than 1, right? Then AK, let's just go to 1, converges absolutely. Okay, so I'm not gonna prove this, but I'll give you the big hint for it. Okay, so if this thing converges, so let L be the limit of this thing. Right, 7 from k equals 1 to n minus 1. A k plus 1 over ak, right? So if that's that limit of that thing above, then this is also true. Okay? And this is, of course, the ratio test. So if that thing, right? So the question says, hey, if that limit is less than 1, show that this converges absolutely. Show that this, this thing is true. And I mean, that is the ratio test. And its limit is something that's less than 1. So your series converges absolutely, right? And the reality is there is nothing special about these terms. You could actually just have said, and then this just becomes and this is actually an if and only if. You know what I mean? So what you can actually do instead is show that AN converges to L if and only if that converges to L. Okay, and that would be a phenomenal exercise for you to all to try. Really, really good, important exercise. Okay, and again, really, it's going to come down to this fact that, you know, this thing converges. So what I want to say here, let's see if I can give you a hint on Q2. Well, Q2, so it's a, right? What's the derivative of log, what notation did I use here? Log P of X, right? So this is just a P-fold composition of logs. So what do you get? You get like 1 over log to the P minus 1 of X times the derivative of log P minus 1X. Do you know what I mean? And then so you get a log P minus 2X here, et cetera, et cetera, et cetera. So the hint is, you know, what is this thing? And when you do that, you'll see it show up in problem 2. And then problem 2, it becomes, you know, it's a one-liner. You basically just apply the integral test and you're done. Okay, sound good? Yeah, I would. You strictly speaking don't have to, but it becomes very straightforward if you use the integral test, right? There is a way around it, where you don't. So I actually got this problem from Rudin, I think, but Rudin doesn't do it using the integral test. And I'm like, this is trivial to do it using the integral test. So totally do it using the integral test. All right, everyone. So that's that. Hopefully that helps you out. Q2. I mean, like, yeah, this will be the last one though. Okay, so 13 Q2. Let's see. Okay, so a sequence such that its odd subsequence converges, but it does not. I mean, yeah, like you can very much just cheat and say, so for A, right, what I would do is I'd say, oh, you know, A2K, so the odd sequence is 0, and then the even sequence is like n. You know what I mean? So you get like 0, 1, 0, 2, 0. Well, actually, I guess. No, I was right. Let's start at 0. Let's start at the odd thing, right? So this is k equals 0. So 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, right? So the zeros certainly converge. The odd subsequence converges because it's just zeros, and the even sequence does not, right? Because it's definitely just shooting off to infinity. So overall, the sequence doesn't converge. For B, show that both the even and odd subsequence converge with the same limit if and only if an converges, right? So for B, this direction is trivial, right? So this direction says if you know the sequence converges, show that the subsequences converge. But we have a theorem that says this, right? You're a convergent sequence if and only if all of your subsequences converge and you have the same limit. Now, the forward direction is a little bit different, but it's basically, right. So you just straight up epsilon delta this. So you want to show an minus L is less than epsilon. Well, you know, since both your even and odd subsequences enumerate every single element of your sequence, if you go far enough into your even sequence, you can guarantee this is true. And if you go far enough into your odd sequence, you can guarantee that this statement is true, right? So just choose the maximum of those two n's, right? There's an n even and there's an n odd. And if you're beyond that, well, this is now true for every n because every single element of your sequence is even in either in your even subsequence or your odd subsequence. And so you're done, right? Like you've gone far enough to ensure that this happens. And in C, so you're told an goes to 0. If Sn denotes the partial sums, show that Sn converges if and only if. Okay, yeah, so Sn, what do I want to say here? So S 2n plus 1. Well, here, maybe we should do Sn. So it suffices to show, right? We know that S2n plus 1 converges. It suffices to show that the even partial sums converge. Right? And in the limit, therefore, we get S2n is the limit of S2n minus 1 plus the limit of A2n. This thing is 0. So the even subsequence converges to the same thing as the odd subsequence does. And by part B, therefore, Sn converges. And we're done. Does that make sense? We're good? Yeah, or at least I think that's probably the easiest way. Like I said, right in part B says your sequence converges if and only if both your even and your odd subsequences converge to the same thing. So in part C, all I have to do is show that the even subsequences converge to the same thing as the odd subsequence. But the only difference between the even and the odd subsequences of partial sums is that each time, right, we know that Sn plus 1 is just always equal to Sn plus An. These things are getting smaller, right? These things are going to 0. And when you set this up, one of these will always be even, right? An even index, and the other will be an odd. So we have this very strong relationship between the even and the odd subsequences that we don't have in part A, right? In part A, I can totally separate how the even and the odd subsequences are behaving. But in part C, I get this relationship between the even and the odd subsequences because they're partial sums. So the fact, I do have to throw in an extra condition here, namely that the thing that relates them, the glue, this subsequence A sub n, is getting smaller and smaller and smaller and really is failing to contribute. But once I know that, I get that the even and the odd subsequences have to basically be doing the same thing, right? Because the difference between them is only the A sub n, and the A sub n is going to 0. So it's really not contributing in the long run. Okay. All right, everyone. So yeah, no problem. Hopefully that makes sense. It was a little bit of sort of like really, really fast, but, bug your classmates too, because I'm sure they, I'm sure you all have good questions too that you can ask each other that you've solved. So definitely, right? You all should be studying together and making study groups and working together. But otherwise, yeah, keep an eye out. So tonight there's going to be a test. It covers everything up to and including last Thursday, but I'm sure you know that because we're 6 tests in by now, right? It's been the same every time. Yeah, and good luck. So have a good weekend, because I probably won't see you before that. I'll see you on Tuesday. There's a good chance Tuesday is the last lecture. We'll see though. We'll see. All right. Thanks everyone. Good luck on your test. Have a good weekend. And I'll see you on Monday or Tuesday.